a fiberglass that is dispersed on an epoxy resin. Now, what is special about electrons, and why do we need to use it for microscopy? Well, the answer is, if you look at the curve, the blue one, this is actually the wavelength of the source. So if, let's say, we're using a light as a source for microscopy, this is the illustrative wavelength. But if we use the electron beams, obviously the wavelength of electrons is much smaller than the wavelength of the visible light. Because of the small wavelength of the electron beam, it allows a very, very small dimensions to be able to image correctly. So it's important to be able to image correctly a very small dimension so that you can analyze and get a good analysis to your specimen. Now, this is how a scanning electron microscope operates. First, you have a gun, and the gun contains a filament. So in this case, it contains a tungsten filament. The reason it uses tungsten is because tungsten has a very high melting point, over 3,400 degrees Celsius. So even if you supply high accelerating voltage to tungsten, it won't melt. So when the tungsten is supplied with accelerating voltage, the tungsten will be heated. And when it gets heated, it will generate lots of electrons. Now that electrons will pass through or be passed through to the electrode, and that electrons will be controlled by the electrostatic lenses. So this is quite different from an optical microscope, because optical microscope uses ordinary mirrors and lenses, but electrons cannot be controlled by ordinary mirrors and lenses. The only way to control electrons is by the use of a magnetic or electrical field. For this reason, the SCM is actually equipped with electrostatic lenses that is part of the column after the electron gun. So these electrostatic lenses inside the column is responsible for controlling the electron beam. When we say control, the beam is reduced into a smaller spot, which is important for generating high magnification image. And the second function of the electrostatic lens is to move the beam across the X and Y. So it's called, that process of movement of the beam across the X and Y is called rasterization. In layman's term, it's called scanning. For this reason, the SEM is called a scanning electron microscope. Now, when the electron beam hits the surface of your sample, the sample will interact with it and will generate different types of signal. Those different types of signal contains important information about the specimen. And in order to take or analyze those informations, a detector must be attached to the SEM itself. So there are different detectors. It can be detectors for simple imaging, like secondary electrons or backscatter electron detector, or it can be an X-ray detector for elemental analysis. Now, this is how the a floor type scanning electron looks like from the outside, although we're going to show it in a live demonstration to you more closely. But I'd like to show you that this is the electron gun containing the tungsten filament. This is the column where the electrostatic lenses is located. And this is the example of the detectors that are collecting the informations from the specimen and transform that information into an image or an elemental spectrum. Now, SEM has many different capabilities, and the most common is the topographical information about the sample. So when we say topography, we're just interested in the surface features of an object, how it looks like, its texture. So is it rough? No? So when we define those features, it's called topographical information. Another type of information informations from the SEM is called the morphological information. So this time, you're describing the size, the shape of the particles that makes up the object. So this is a very timely example. This is a fiber of the mask, and you'll see that, of course, the fiber is it has a dimension, it has a diameter. So when you speak about that, you're talking about the morphological information. Another capability of the SEM is a compositional analysis. So in this case, it utilizes the energy dispersive X-ray spectrometer. So what the EDS do is to determine the presence of any elements from the periodic table, usually from boron to uranium, beryllium to uranium, and just by simply defining the area of the sample that you wanted to analyze, the instrument can readily gives you and identify the presence of the elements. So in this case, we have here a secondary electron image, a BSE image, and then it maps out in color, software colors based on the preferential color by the user. So in here, we intentionally colored yellow, the copper. We intentionally colored yellow, the nickel. We intentionally colored violet for lead. And then we integrate all those informations into one mixed data. So this is called an elemental mapping. Don't worry, we're going to show that to you in the live demonstration. Or you can only simply identify the elements that are present. All you have to do is draw a box, draw a line, specify a point, and the instrument, the software will give you the elemental identifications of your specimen. Or if your SEM is equipped with electron backscatter diffraction detector, just like ours, you can use the EBSD for crystallographic analysis. So in this case, we may be familiar that some metal alloys has corresponding phases. For steel alloy, they have ferrite phases, they have cementite phases. The electron backscatter diffractions attached to your SEM has the ability to analyze those phases. Or you can also use micro CT scan. You may be familiar with CT scan for medical application. But there's also